This is lecture 6. Today we're going to finish talking about chapter 3. I'm going to start by solving some initial value problems using the theory that we developed last week. We will look at another way to find a particular solution to a second order linear differential equation. And then in the final section today, we will extend our ideas to higher order linear ordinary differential equations. Before I begin, let me remind you that there's a midterm exam at 2 o'clock next Wednesday. So let's solve some initial value problems. We're going to be looking at things like this. AY double prime plus BY prime plus CY is equal to GT, where A, B, and C are numbers and G is a function. And we will have two initial conditions. Y at some time t0 is equal to y0, and y prime at some time t0 is equal to another number, y1. To solve an initial value problem like this, the idea is, first, we need to find the general solution to the homogeneous equation a y double prime plus by prime plus cy is equal to 0. We need to find a particular solution to our differential equation. Two possibilities here. If GT does not solve the homogeneous equation, and if we have a complicated function, we'll look at each part separately, then our ansatz should look like GT. But if the function GT does solve the homogeneous equation, then we're going to use the trick of multiplying by t. And if necessary, we can multiply by t a second time, a third time, etc. Step 3, we're going to add these two functions together. And then finally, in step 4, we're going to find the constants C1 and C2 to satisfy the initial condition. So to say that again, steps 1, 2, and 3 are all about finding the general solution to our non-homogeneous equation. And then only after we've done that do we look at the initial conditions and use them to find C1 and C2. We need to do step 4 last. We need to get our general solution first before we start finding C1 and C2. If we do these steps in a different order, we might get the wrong answer. For example, let's suppose I want to solve y double prime minus y is equal to 2e to the power t with the initial conditions y of 0 is 1, y prime of 0 is equal to 2. First, I'm going to do the correct solution. I'm going to do step 1, then step 2, then step 3, then step 4. I'm going to do the steps in the correct order. How do we find the general solution to the homogeneous equation? We start with the characteristic equation. We find the roots of the characteristic equation, and then we can just write it down. In this case, C1 e to the power t plus C2 e to the power minus t. And then step 2, we need to find a particular solution. Now, we can't use a e to the power t because this solves the homogeneous equation. So we're going to use our trick. We're going to multiply by t. Instead of looking at a e to the power t, we multiply by t. The ansatz we're going to use is a t e to the power t. Differentiate this 2 times and then put into the differential equation. We're going to find that we must have 2e to the power t is the same as 2a e to the power t. So clearly for this example, a must be 1. So our particular solution is t e to the power t. Okay, step 3, add them together. Underlined in orange, I have the general solution to the homogeneous equation, and then underlined in red, we add on a particular solution to the non-homogeneous equation. This is the general solution to the differential equation. After we've found this, we can find the constants C1 and C2. And I'll go through this very quickly. Because the derivative of y is C1 e to the power t minus C2 e to the power minus t plus e to the power t plus t e to the power t, when we replace t by 0, we end up with 1 is equal to C1 plus C2, and 2 is equal to C1 minus C2 plus 1. That tells us that C1 must be 1 and C2 must be 0. So then we can write down the solution to the initial value problem. E to the power t plus t e to the power t. I'm going to write this at the top for the time being, because we're going to be looking at this again. Now let's solve this again, but let's do this incorrectly. And this is something I've seen students do quite often in the exams. Don't fall into this mistake yourself. Step 1, find the solution to the homogeneous equation. This is exactly the same as before. I've just copied and pasted it just here. This part is correct. After step 1, let's do step 4. Find the constants C1 and C2. Do the same calculation as before, but this time, because we haven't found a particular solution yet, we're looking at a different function y. And so we end up finding the constants. C1 is 3/2 and C2 is -1/2. After step 4, let's do step 2. Find a particular solution. This slide is correct. This slide is just a copy and paste of the previous one, so we don't need to spend time just here. And then after step 2, do step 3. Add the two solutions together. 3/2 e to the power t minus 1/2 e to the power minus t plus t e to the minus t. But remember, the correct answer to this question is e to the power t plus t e to the power t. Why is this wrong? Because it doesn't satisfy the initial conditions. It satisfied the initial conditions before we added on the particular solution. But as soon as we add on plus t e to the power t, it no longer satisfies the second initial condition. So doing step 1, then step 4, then step 2, then step 3 gave us the wrong answer. We need to find the general solution to the non-homogeneous differential equation first, and then only right at the end of our answer do we look at the initial conditions to find C1 and C2. Let's do another example. This one's a little bit more complicated. Solve minus y double prime plus 6y prime minus 16y is equal to 1 plus 6 e to the power 3t sine 2t, with the initial conditions y of 0 is 15/16 and y prime of 0 is equal to -1. This is actually an exam question which I asked a number of years ago in actually a slightly different course. It was a third-year course back then. Back in 2013, I gave students 30 minutes to solve this question. Test yourself, see how long it takes you to answer questions like this. Could you solve a question like this in 30 minutes? So to solve the differential equation first, we'll look at the initial conditions right at the end. We don't want those yet. We're just going to look at the differential equation. To solve this, we're actually going to look at three different equations. First, we're going to look at the homogeneous equation equal to 0. Then I'm going to look at the non-homogeneous equation, but only with the first part, only with the 1. And then finally, I'm going to look at the non-homogeneous equation, but with the second function, 6 e to the power 3t sine 2t. And then after we have the general solution to the green equation, a particular solution to the orange equation, and a particular solution to the blue equation, we're going to add them all together. So first, let's look at the homogeneous equation, this green equation. We need the characteristic equation. Minus r squared plus 6r minus 16 is equal to 0. And this has roots 3 plus or minus I square root of 7, which I leave for you to check. As soon as we know this, we know that the general solution to this green homogeneous equation must be constant, e to the power 3t, because there's a 3 just here, sine root 70, because there's a root 7 just here. And then the second function is the same, except we change sine to cos. And it doesn't matter if we do sine first or we do cos first. It doesn't matter. If we wanted to, we could put cos first and then sine second. Next, we look at the first one of the two non-homogeneous equations. This is just equal to 1. 1 is just a number, so our ansatz is just going to be a number. So we're going to be looking at the ansatz, say capital Y is equal to some number C. And then we see that on the left side, or what was the right side, we have the number 1. Y double prime must be just 0. Y prime must be 0. We get minus 16c on the right. So of course c is minus 1 over 16. And then let's look at the blue equation, our second non-homogeneous equation. We need to find a particular solution to this equation. Now what do we have here? We have a number multiplied by e to the power 3t multiplied by sine 2t. So our ansatz is also going to have number e to the power 3t sine 2t. Anytime we have sine, we must also have cos. So we also need a number e to the power 3t cos 2t. I'm not showing all of the details here. I'll leave this for you to double check. If we differentiate this ansatz 2 times and substitute in, the right-hand side simplifies to e to the power 3t cos 2t multiplied by minus 5a plus e to the power 3t sine 2t multiplied by minus 3b. And because this must be the same as 6 e to the power 3t sine 2t, a must be 0, and minus 3b must be 6, so b must be minus 2. So we have our particular solution, minus 2 e to the power 3t sine 2t. And then we add these three functions together. The green function is the general solution of the homogeneous equation. And then we found particular solutions to two different equations. We add these on. Minus 1 over 16, and then the one we just found, minus 2 e to the power 3t sine 2t. There's only one step left, the step that we must do last. We need to find the constants C1 and C2. Here's the calculation. I'm not going to dwell on this. I'll leave this for you to reread later and double check. I think, and check if I've made a mistake here, I think that we want C2 is equal to 1 and we want C1 is equal to 0. So assuming I haven't made a mistake here, we can write down that the solution to the initial value problem is e to the power 3t cos root 7t minus 1 over 16 minus 2 e to the power 3t sine 2t. So I ask you again, do you think you could solve this problem in 30 minutes? Now, we've been using the method of undetermined coefficients to find a particular solution. And this method works well as long as the function gt is a nice function. Oh, there's a typo here. This should be e to the power kt. I'll fix that later. So if we have a nice function like an exponential function, a sine, a cos, a polynomial, or some combination of nice functions, exponential function multiplied by cos, still a nice function. If we have nice functions like this, then we can use the method of undetermined coefficients and everything works nicely. However, if gt is not a nice function, then we might need to use a different method to find a particular solution. And that brings us on to the method of variation of parameters. This is another method to find a particular solution. And this is the method that we're going to want to use if we have a complicated or not nice function gt. For example, find a particular solution to 3 cosec t, or if you prefer, 3 csc t. Now, cosec is not a function I would call a nice function because differentiating it changes to a different function. We can't differentiate cosec and still get cosec like we can with sine and cos. So we can't use the method of undetermined coefficients. We need a new method. And the idea goes like this. We know that the general solution of the homogeneous equation is c1 cos 2t plus c2 sine 2t. We're going to replace these constants by some unknown functions. Let's say u1t and u2t. And then we're going to try to find u1 and u2 so that capital Y solves to a similar idea to an idea we've done in reduction of order. Key thing to note here is there's going to be lots of u1 and u2 that we could use. In fact, there's infinitely many pairs of u1 and u2. And we only need to find one pair of functions which work. So it's going to be okay for us to add in an extra condition whenever we want. We're not trying to find every possible u1 and u2. We're just going to try to find one pair which works. So let's suppose that we start with the ansatz. Capital Y is u1 cos 2t plus u2 sine 2t for some functions u1 and u2. We can differentiate this. Now, it's getting complicated. We've got 4 terms already. When we differentiate again, we'll have lots more terms. Remember I said we can add an extra condition whenever we want. So let's do that now. Let's use our chance to add an extra condition. And let's just suppose that these red terms are equal to 0. So that simplifies a little bit, and then we can differentiate again. And now y double prime only has 4 terms. And then we substitute into the differential equation. On the left side, we have 3 cosec t. On the right side, after we've substituted in and cancelled, we end up with minus 2 u1 prime sine 2t plus 2 u2 prime cos 2t. So let's recap. We want to find u1 and u2, which satisfies 2 equations. Instead of one complicated equation, we've made an extra condition. So now we have 2 simpler equations to satisfy. The green equation came from the differential equation at the top of this page, and the red equation was this extra condition which I invented on the previous slide. If we can find u1 and u2 which satisfy these equations, then we're done. We have our answer. From the second equation, from the latter equation, we can rearrange this to find that u2 prime is minus u1 prime cos 2t divided by sine 2t, and then we can substitute this into the first equation. And rearrange, and the first equation then simplifies to u1 prime is equal to minus 3 cos t, which I leave for you to check. After we know u1 prime, remember u2 prime is minus u1 prime cos 2t sine 2t, so then we find that u2 prime must be 3 over 2 cosec t minus 3 sine t. Now we know u1 prime and u2 prime, we can integrate to find u1 and u2. So here we are. u1 is the integral of u1 prime, that's the integral of minus 3 cos t, which is minus 3 sine t. We don't need a plus constant here because we're not trying to find every possible u1, we're just trying to find one which works. So if we can forget about the constant of integration. And u2 is the integral of u2 prime. And if you remember your first year calculus, you will remember that the integral of cosec is natural logarithm of the absolute value of cosec t minus cotan t. And of course, the integral of minus sine is plus cos. So now we have u1 and u2. Now we know our particular solution. u1 cos plus u2 sine. Put these in, simplify a little bit, and we get the answer 3 sine t plus 3 over 2 natural logarithm of the absolute value of cosec t minus cotan t sine 2t. This is a problem which we could not solve using the method of undetermined coefficients because we have these complicated functions. But we can do it using the method of variation of parameters. So let me summarize the method here. Let's suppose we know that c1y1 plus c2y2 is the general solution to a homogeneous differential equation, and we're trying to find a particular solution to a non-homogeneous equation. Step 1 is we make a guess. We guess that the particular solution is u1 y1 plus u2 y2, where instead of constants now we have functions of t. We're going to make an extra condition, and it's always the same extra condition. We're always making the extra condition that u1 prime y1 plus u2 prime y2 is equal to 0. we're going to put capital Y into our non-homogeneous equation, and we're going to find equations for u1 prime and u2 prime. We'll solve these equations to find u1 prime and u2 prime. We integrate to get u1 and u2, and then we know our particular solution. Let's do an example. Find a particular solution to y double prime minus 2y prime plus y is equal to e to the power t, natural logarithm of t. Natural logarithm is not a nice function. If we differentiate natural logarithm, we get 1 over t. We don't get the same type of function. So we can't use the method of undetermined coefficients. We need to use the method of variation of parameters. First, we need the general solution to the homogeneous equation. We know how to do this. In this case, it's c1 e to the power t plus c2 t e to the power t. Our ansatz is going to be the same function, but with the constants replaced by functions. Our ansatz is going to be u1t e to the power t plus u2t t e to the power t. We need an extra condition. The extra condition is always that u1 prime y1 plus u2 prime y2 is equal to 0. And for us, for this example, our extra condition is going to be u1 prime plus u2 prime t is equal to 0. Anytime we see this, anytime we see u1 prime plus u2 prime t, we can just replace this by 0. So here's the calculation laid out. I'm going to fill in each line as we talk through it. We start with y is u1 e to the power t plus u2 t e to the power t, and we differentiate this. But remember, u1 prime plus u2 prime t is equal to 0. So these two terms we cancel out. And we're left with u1 e to the power t plus u2 e to the power t plus u2 t e to the power t. And then we differentiate again. u1 prime e to the power t plus u1 e to the power t plus u2 prime e to the power t plus u2 e to the power t plus u2 prime t e to the power t plus u2 e to the power t plus u2 t e to the power t. And again, we can cancel some terms, because u1 prime plus u2 prime t is equal to 0. That's our extra condition. So we end up with y double prime is u1 e to the power t plus u2 prime e to the power t plus 2u2 e to the power t plus u2 t e to the power t. Okay, now we substitute these into the differential equation. And then we're going to look to cancel some terms. Here's a u1 e to the power t, another u1 e to the power t, but then minus 2 u1 e to the power t. These are going to cancel out. What else do we have? There's 2u2 e to the power t here, and minus 2u2 e to the power t just here. These are going to cancel out. There's a u2t e to the power t, another u2t e to the power t, and then minus 2 u2t e to the power t. These are going to cancel out. What are we left with? We're left with u2 prime e to the power t. And then, of course, e to the power t's are going to cancel. And we're left with u2 prime is equal to the natural logarithm of t. Remember, our extra condition was that u1 prime plus u2 prime t is equal to 0. Rearrange that. Now that we know that u2 prime is natural logarithm of t, u1 prime must be minus t natural logarithm of t. We're going to integrate these. Here they are. We need to remember how to integrate t, natural logarithm of t, and natural logarithm of t. After we know u1 and u2, we're finished. We can then write down the particular solution. For this example, the answer is a half ln t minus 3/4 t squared e to the power t. Okay. So that's quite a complicated, quite a difficult idea. Isn't there an easier way to do the method of variation of parameters? We have a theorem which simplifies things a little bit. We're still going to have to do the same work. We're still going to have to do the same integrations, but it's perhaps easier to remember this theorem than the previous method. Let's suppose we start with a fundamental set of solutions to the homogeneous equation. There's a typo here. Y double prime this should be. I'll make a note of that. Suppose we know a fundamental set of solutions to a homogeneous equation, then we can find a particular solution to a non-homogeneous equation as follows. We want the equation minus y1 integral of y2g divided by w plus y2 integral of y1g divided by w, where w is the Wronskian. And this formula is perhaps easier to remember. It doesn't necessarily make the calculation any easier because we still have to do two integrals, whichever method we use, and it's still going to be exactly the same integrals, but it maybe makes our calculation a little bit quicker if we go straight to this formula. Before I go on, it doesn't matter which function you call y1 and which function you call y2. Let's suppose you swap y1 and y2. Then in the Wronskian, you're also going to be swapping the positions of y1 and y2. So we're going to be multiplying the Wronskian by minus 1. Remember your linear algebra, what happens to a determinant if you swap two columns of a determinant? The determinant is multiplied by minus 1. So then we get an extra minus. This minus turns to plus, and this one turns to minus. And then the minus signs cancel out, and you get exactly the same answer. So this is why it doesn't matter which function you call y1 and which function you call y2. Okay, let's solve an example using this theorem. And let's do the same one as we just did. Find a particular solution to y double prime minus 2y prime plus y is equal to e to the power t natural logarithm of t. First, we need a fundamental set of solutions. So first we start with a characteristic equation. We find repeated root 1. Therefore, our fundamental set of solutions are e to the power t and t e to the power t. Okay, then we need to calculate the Wronskian. The Wronskian is the determinant of the 2 by 2 matrix y1, y2, y1 prime, y2 prime. Put y1 and y2 in, calculate the determinant, and we find e to the power 2t. Then we're ready to start using the formula from the theorem. So let me just recap what we have so far. Here's the formula that we want to use. The particular solution that we're going to find is minus y1 integral of y2g divided by w plus y2 integral of y1g divided by w. And our functions are at the top. y1 is e to the power t, y2 is t e to the power t, function g is e to the power t ln t, and the Wronskian of y1 and y2 is e to the power 2t. I'm going to calculate this particular solution just on this slide. Put these functions in. And then we can see some of these terms are going to cancel. E to the power t divided by e to the power 2t, these are going to cancel. And in the second term, e to the power t on top, e to the power 2t on the bottom, these are going to cancel. So we end up with minus e to the power t, integral of t ln t, plus t e to the power t, integral of ln t. Think back to the previous time we solved this. Last time we had to integrate ln t and we had to integrate t ln t. We're doing exactly the same integrals here. We're not really saving work in the integration. We're just saving some work at the start, solving the two equations to find y1 prime and y2 prime. So after we've calculated these two integrals and then simplified a little bit, we end up with exactly the same solution that I found in the previous example. If I give you a method of variation of parameters question, it's completely up to you which method you use, as long as you explain which method you're using, how you're doing it, etc. If you want to use this formula, that's fine. Just say, I'm using this formula from the lectures, and then use it and show me how you use it. For the rest of today's class, we're going to be extending the ideas that we've developed over the last 2.5 lessons to higher order equations instead of just second order equations. For example, let's suppose I gave you a fourth order homogeneous linear differential equation in an initial value problem with some initial conditions. This is a fourth order equation because the highest derivative is 4 And if we have a fourth order equation, we need 4 initial conditions. How do we solve this? First, we start with the characteristic equation. That's r to the power 4 plus r to the power 3 minus 7r squared minus r plus 6 is equal to 0. A little bit more complicated to find the roots of this than a second order equation, but not impossible. The roots of this equation are 1, minus 1, 2, and minus 3. As soon as we know the roots, we can write down the general solution to the differential equation. From 1, we have e to the power t. From minus 1, we have e to the power minus t. From 2, there's e to the power 2t. And from minus 3, we have e to the power minus 3t. Now here's this number 4 again. Fourth order equation. 4 initial conditions. 4 roots to the characteristic equation. And therefore 4 functions and 4 constants. After we found the general solution, we need to find the constant C1, C2, C3, and C4. Another typo just here. There should be a number 4 just here. So we differentiate y 3 times, replace t by 0, and we obtain a linear system of 4 equations in 4 unknowns. You know how to solve this from linear algebra, so I'll just tell you the answer. C1 must be 11 over 8, C2 must be 5 over 12, C3 must be minus 2 over 3, and C4 must be minus 1 over 8. As soon as we know the constants, we can write down the solution to the initial value problem. Another example, solve 4 derivatives of y minus y is equal to e to the power of t. This is a non-homogeneous fourth order linear ordinary differential equation. We start with a characteristic equation. 0 is equal to r to the power 4 minus 1, or r squared minus 1, r squared plus 1. And it's simple to see that the roots must be 1, minus 1, I, and minus I. After we know these roots, we can write down the general solution to the homogeneous equation. From r1 equal to 1, we have e to the power t. From r2 equal to minus 1, we have an e to the power minus t term. And let's do the last two together. We have I and minus I. That gives us the terms cos t and sin t. Next, we need to find a particular solution to the non-homogeneous equation. And I'm going to use the method of undetermined coefficients. I'm going to look at this function is e to the power t, so our ansatz must include e to the power t. But look, we have e to the power t just here. So we can't use e to the power t. We need to try a function involving t e to the power t. So the ansatz is going to be some number capital A t e to the power t. Then differentiate 4 times, and then substitute into the equation. We have e to the power t is equal to 4a e to the power t. So of course a must be a quarter. Our particular solution is a quarter t e to the power t. And then we're just going to add these two solutions together. First, the general solution to the homogeneous equation, and then we add on our particular solution. So just the same ideas that we've been using for second order equations. Let me just remark that anytime the characteristic equation has a repeated root, we just multiply it by t. So for example, let's suppose that we have a sixth order equation, and let's suppose that the roots are 7, 7, 7, 7, 7, and 8. From R1 equal to 7, we're going to have e to the power 7 t10. The second root is the same. The second root is also 7. So our second function is going to be t multiplied by e to the power 17. We did that earlier in this chapter. If the third root is also 7, same idea, just multiply by t. So now t squared e to the power 17. If the fourth root is also 7, do the same thing, multiply by t. Now our fourth function is t cubed e to the power 70, and so on. If we have R5 is 7, then again, multiply by t. Our fifth function will be t to the power 4 e to the power 70. And then the sixth root is a different number, so we can just forget about the t's and go back to just e to the power 8t. Perhaps we want to go backwards. I suppose instead of starting with a differential equation and then being asked to find the solution, let's suppose we go the opposite way. Let's suppose I'm telling you of a solution, and then I'm asking you to find a linear, homogeneous differential equation with constant coefficients, which has this general solution. So it's doing what we've been doing, but going the opposite direction, starting with a solution and then going back to find a differential equation. How can we do this? We need to find the roots of the characteristic equation. First, we have e to the power t, so that's the root 1. And then we have t e to the power t. Again, that corresponds to the root 1. And then we have e to the power 2t and sine t, and e to the power 2 cos t. But that corresponds to the root 2 plus or minus I. What do we then have? We then have e to the power 2t sine t and e to the power 2t t cos t. That's the same as what we just have, but now multiplied by t. So again, that must also be corresponding to the root 2 plus or minus I. So the characteristic equation should look like this. Just looking at the part in the purple rectangle first of all. First, we have the root 1, so there's going to be an r minus 1 term. Because this is repeated, it's going to be squared. And then we have 2 plus I and 2 minus I. For 2 plus I, we would have the part r minus 2 minus I. And because it's repeated, squared. And 2 minus I, that gives us the bracket r minus 2 plus I, because minus minus is plus. And again, because it's a repeated root, this is squared. Multiply all of this out, and I leave this for you to check. We obtain r to the power 6 minus 10 r to the power 5 plus 43 r to the power 4 minus 100 r cubed plus 131 r squared minus 90 r plus 25. Now we know a characteristic equation. It's straightforward to write down a differential equation which has this characteristic equation, because of course we just use the same numbers. Instead of 1r6, we would have 1 d6y dt to the power 6. Instead of minus 10 r to the power 5, of course we have minus 10 and then 5 derivatives of y. Instead of plus 43 r to the power 4, we have plus 43 and then 4 derivatives of y, and so on. And because it's homogeneous, in the end we have equal to 0. This answer is not unique, of course. The question says find a linear homogeneous differential equation, because any constant multiple of our answer will also be a correct answer to this. And then that brings us to the end of today's lesson. That's the end of chapter 3, second and higher order linear differential equations. Tomorrow we're going to start talking about the Laplace transform. Next week there is a midterm exam. The midterm exam will cover chapters 1, chapter 2, chapter 3, and the topics that we will talk about tomorrow. Are there any questions?